from Professor Tayechi. He had the Department of Mathematics at the Dean and the head of the undergraduate program at the University of Tunis, and he's visiting us for a few months. And he will talk about the asymptotic behavior for inhomogeneous nonlinear Schrödinger equations. So please.
Thank you, Mohammed, for this introduction. Not the head of the department. I'm just the school doctoral school. Thank you for the invitation. Thank you for giving me this opportunity to talk about this work. It's a pleasure for me. I'm very happy to be with you. And I will give a talk on work with Lesad Alwi from University of Tunis Manar, and maybe the last part with Lesad Alwi and Sirin Jbel. And let me show the plan of this work. So I will give first an introduction, and then I will talk about local well-posedness for the equations. Then we turn to the global existence, and I will consider oscillating data, and then we'll talk about scattering results. And if I have time, I will discuss the damped nonlinear Schrödinger equation. So we will consider the nonlinear Schrödinger equation as it is written. So there is two terms. The standard nonlinear equation is when A is equal to 0 or K of X is equal to some constant, say some complex constant. So here alpha is the power of the nonlinearity, and A is a positive number, which is the damping term, and K is a potential, which may be real or complex, and we say sometimes that is a coefficient. So as I said, in the case where A equal to 0 or K is equal to mu, a constant, this corresponds to standard nonlinear equation. And when A equal to 0, this is the inhomogeneous nonlinear Schrödinger equation. It will be possible to consider these type of potentials. The first one is a regular potential with sigma positive. And the second one is a singular potential. And we may also combine both of these two potentials, so having some singularity at the origin or some decay at the infinity. Okay, this equation has been used by many mathematicians. In particular, Merrill consider the nonlinear Schrödinger equation with potential K, but it is supposed that the potential is bounded by some constant which is finite, and it is strictly positive. And it is also used by Fibishi and Wong. And here the potential K is supposed to be C4 and infinity. And in the case where R is positive, this is the damped standard NLS, and it is introduced by Tsutsumi. I say that this kind of equation appears in diverse branches of physics, such as nonlinear optics or plasma physics. And these are some references to the physical application of this equation. In particular, Fibishi notes that the damping term should be not neglected in the nonlinear Schrödinger equation, and the potential K of X account the inhomogeneity in the medium. Sorry. So the aim of this talk is to study the impact of the potential on the damping and the damping on the local existence, global or blow-up existence of solution, and maybe also on the scattering, and to unify the theory for the NLS and the damped NLS and inhomogeneous damped NLS. For the local existence in the case of standard Schrödinger equation, I may quote the book of Cazenave. There is many other books also. The book of Cazenave, who presents long study or a theory for the ENLS, for the NLS, and he shows that if alpha, it is shown in many papers that if alpha is positive smaller than 4 over n minus 2, the problem of well-posedness for NLS in H1 is well-posed, meaning that for any initial data in H1, there exists a solution for NLS which is continuous to taking value in H1. And that satisfies this Duhamel formulation of the equation, where ET Laplace is the free Schrödinger group. It is given by the convolution with this kernel. For the NLS with this potential, x to the power minus b with b positive, this equation had some scaling. If u is a solution, then u lambda, defined by this power lambda to the power 2 minus b over alpha, is also a solution. And when we evaluate the norm in H dot S of this type of the initial data, we find that there is this equality where SC is the critical Sobolev index given by this n over 2 minus b over alpha, and requiring that S positive and greater than this critical exponent and smaller than n over 2. We find this condition on S, in particular, B should be positive smaller than 2. B is smaller than n, so that x to the power minus b is L1 log. And alpha should be positive, and with this condition, it should be smaller than 4 minus 2b over n minus 2s. And the construction of the solution, say, in general, is done via fixed point argument on the Duhamel formulation. And when looking for the linear part, and if we want to control in L infinity H1, L infinity in time and H1 in space, for the linear part, there is no problem. We have this equality, but when we have to control the nonlinear part, we have to intersect with some LQ, LR space. And when doing this, for the linear part, when we are in the part LQ, LR, we have this inequality, and this inequality is satisfied if we verify by scaling that this equality should hold. 2 over Q plus n over R is equal to n over 2. And this is a necessary condition to have this inequality. And for sufficient condition, we use the Sedgwick's estimates. We have these QR admissible pairs, so satisfying this inequality, equality, and QRN are different from this. We have this inequality, it is satisfied. And we have to estimate the non-homogeneous part of the integral. It satisfies that we have this inequality in L, R1, LP1, and on the other side, L2 prime, P2 prime, all their conjugate exponent of R2 and P2. And this inequality is proved by Sedgwick's for the case Q equal to R, and for Q are different from these exponents by Genever and Velo and by Kiel-Tao for the endpoint case. So if we have K bounded, when we estimate this nonlinear term, we can use directly some particular admissible pairs, gamma and rho, so that directly we have this inequality and we have to close the fixed point using particular value using this inequality. But for the NLS, we cannot use the same framework because K we do not belongs to Lebesgue spaces. So we have to use another idea to control this part. And this begin with Juno Stewart for the case of alpha positive and smaller than form minus 2p over n minus 2 by dividing the power x to the power minus d in two parts. The first part is near the ball and the second part at the exterior of the ball, but we cannot reach the critical exponent. Here is strictly smaller than 4 minus 2b over n minus 2. And by applying abstract results, they prove the local existence and the critical case is not treated and there is no regularity property. And for after that, Guzman, using the same idea, he construct local existence result, but in the case of alpha strictly smaller than 2 minus b. Okay, thank you. Smaller than 4 minus 2b over n minus 2, and still not reaching the critical case. And he used Stuttgart estimates on the Lebesgue space. After that, it is improved by Dean. And in 2021, Kim Lee So, based on some circuits, it's based on Lebesgue space, they reach the critical case, but there is no blow-up criterion and no continuous dependence results on the initial data. And there is no result also on conditional uniqueness. So as I said, the proof is based on Stuttgart estimates in weighted Lebesgue space. In fact, they combine Stuttgart estimates with smoothing effect of Kato-Yajima. And these are the spaces used by Kim Lucio. And the result in these spaces with some gamma Schrödinger admissible pairs. But as I said, they do not unify with the case B equal to 0. And there is no complete theory for this local well-posedness. And even for the global theory, it is not simple to continue the study for this equation. And what we propose with Alvi is to handle the singular potential with Lorentz space. Lorentz space are real interpolation between L1, L infinity with this manner. And also we have the fact that x to the power minus b is in the Lorentz space Ln over b infinity. And this pi space give a good refinement for the Lebesgue spaces. For example, when we take p smaller than 2 numbers and greater than q1, we have this embedding. LPP is the usual Lebesgue space LP, and it is increasing with respect to the second space, the second index. There is no index in this Lorentz space. The Holder inequality and Young inequality holds in Lorentz space. For the Young inequality, it is the same as for the Lebesgue space, and for the second index, it is as in for the Holder inequality. And we have this Sobolev Lorentz space we may define this Laurent space. The difference here is that we require that this is in LPQ, in the Laurent space. We have also a good embedding H1 in L2 over n minus 2, but gamma 2, which is embedded in the large space L2 over 2n over n minus 2. Another interesting thing that the scaling is the same as for Lebesgue spaces, and the second antics have no effect in these for these spaces. And in Laurent space, also we have the Sylkart's estimates, which are done here and out. And this is for the homogeneous part with 2 here, and this is for the inhomogeneous part here.
I'm sorry, so how do you define the Laurent space?
Laurent space is, there is 2 definitions which are equivalent. This one is by real interpolation, and there is another one with rearrangement and some norm of the rearrangements. So this. Now we have to do the local existence, and we have to choose 2 particular pair, a particular pair, Sylkart's pair, rho and gamma. Rho is for the space, and gamma is for the time. And you see here the appearance of B depending which is related to K. And to choose these, this pair of Sylkart's, we have to verify that we have this embedding between the W dot S rho 2 into W dot S rho prime. And we have this result on local. So B should be smaller than this is. 2 is already seen. And we have this condition, which is n minus 2s. And we have the, say, the similar results as for the standard Schrödinger equation. The only distinction here is the appearance of B. So local existence intersected with space L gamma.
Question. This is for DI-NLS, right? Then inhomogeneous nonlinear Schrödinger.
No, this is for the ENLS, but it is the same for the damped with the A. It will be
Because
this
you have to put some condition on K as well, right?
on.
K.
Yeah. This is for the inhomogeneous equation.
So Slim, there your current is still X minus B, or we can extend the.
Yeah. Exactly. For any K in L and over B, yes.
And you need it is regular, no need to be regular.
No,
You don't-
no need. I don't know.
And for S is 0, so this is the maximum L2, and for L2 we need something more, or? So
For-
for Schrödinger, sometimes Schrödinger needs some for the blow-up criterion because it's critical space.
Yes. For L2, we have
The
the,
result is HS, no? So
yes,
we can go
even
to
for
S.
S equal to 0, yes.
Can shrink B to 0 there, or? You constant there? Because the curve is X minus B.
Yeah. Just 1 minute. No, just 1 minute. Yeah, effectively, here I write K equal to X minus B, but this is to explain all these exponents, how they appear, the critical case. But it applies for K of X smaller than. By the way, here I have no damping term, but it will works as it is, there is damping term. This is your question?
Yeah.
Yeah, Tawfiq. So, yeah, here there is only K of X. There is no, sorry. Yeah, can take S equal to 0 here, and your question of
Just to see your link to standard Schrödinger equation when B is going to 0. So that
yeah. When B is equal to 0, so we are in Ln over B gamma infinity, taking B equals 0, we are in L infinity. So you see K is like something in L infinity.
Your blow-up criterion is connect to Srikard's estimates or because it's critical space. So we need
Yeah. For this, the criteria is connected to these Srikard's. Yeah.
So
Yeah.
when you define
But by the way, we have another criterion. If we are strictly smaller than this. No, where we are. Sorry. We have the rate of the blow up. Yeah. We have this if alpha is greater than each dot S for S equal to 0 is L2. Here, the coefficients are complex, not really complex. And we have all this theory, the same as L2. And here we have the lifespan, estimate of the lifespan, meaning that here is the norm of U naught in each dot S, I think. We measure the lifespan with some lambda, but it is we can replace lambda by lambda, the norm of U naught in H point S.
So you're taking the alpha to be less than that quantity such that that exponent over there is what? Positive.
Positive, yes. For these both, for this and this. So when the initial data became small, this goes to infinity. Yeah. So some comments that we have also unconditional result on unconditional uniqueness. And this result also improved the results by showing that the solution becomes in these spaces with gamma 2, which is a smaller space than this. And we have some also property on Tmax and the maximal time of existence. And these results, as I said, there is a problem when n is equal to 3. We here we cannot reach n. We cannot reach 2 in terms of b when s equal to 1, and b is smaller than 1. So we can improve this by obtaining some results when b is greater than 1, but we cannot go more than 3/2. Yeah. So as I said, the proof uses the Schrödinger system as fixed point argument in this space, and we construct solution in the intersection with the space, and we can show uniqueness of meaning unconditional uniqueness of the existence. So we may remove the second condition on the existence. In some cases, we can remove this condition because there is a unique solution in this intersection, but we can remove this condition in some cases.
And you also have a global proposals for one data.
Yes. Can make. Yeah, there is results on global existence, and we can show that the maximal time of existence in the case, for example, s equal to 1 depends on the norm of U naught, but in this range, the maximal time of existence depends on the gradient, and we have the other properties for in the case of real potential. We have this property of conservation of mass and energy, and we have as well the same as for the Schrödinger equation for small initial data. So now we are interested by the case where K have some coefficient which is complex, and we are interested by studying the global existence for small initial data. So for this, I recall some results about oscillating data for the standard analysis. And this is done by Kaznav, Weissler, and by Tsutsumi. So taking this type of initial data, dx squared by phi, d is a positive number large. They show that there is global existence when d becomes large. And for this, they introduced the notion of rapidly decay, and the solution is in some LA alpha plus 2, and A is given by this expression related to the nonlinearity alpha. So if this is small and alpha is greater than some alpha naught, then we have global existence. And alpha naught is the positive root of this equation. It is in particular smaller than 4 over n and greater than 4 over n plus 2. So as I say, these exponents are done by some scaling property of the equation. Since our spaces, Lorentz space, have the same scaling property as Lebesgue spaces, so we exploit this property and we introduce these two numbers, Varro and A, and how we choose Varro. We choose Varro so that this mapping apply L rho Q to L rho prime CQ, not necessarily Q over alpha plus 1. And by scaling, if we consider the norm of the initial data in this space, or the norm of in this space LAL rho, we have this relation. And so that this norm is conserved or is the same, or independent of lambda, we have to choose A satisfying this property. And rho we became from this, we find rho and rho prime with this property, and A is given by this. And since we will use this Streetkar's estimate for non-admissible pairs, we will need that A should satisfy that it is smaller than 2 over psi. And this is psi is the with rho is the Streetkar's pair. Streetkar's pair, admissible Streetkar's pair, not non-admissible. This is not admissible. And we this is equivalent. Then this is depends on alpha, and this one depends on alpha. This inequality is equivalent that alpha is greater than alpha naught. So here alpha naught is the critical exponent for this equation with the B. It is the same when B equal to 0 for the Schrödinger equation. And so when B is equal to 0, alpha naught is the known Strauss exponent. And when B is equal to 2, here B equal to 0 and B equal to 2, alpha naught 2 is equal to 0. Okay, so we reach the value 0. And what we show here, we show when n is greater than 4 and Q is the second index in the Lorentz space is greater than 1. So taking an initial data and alpha satisfying this inequality, and the initial data sufficiently small with these oscillations, then we have global existence and these bounds for any admissible pair P. So how we do the proof? So we take zeta and rho admissible pair, and as I say, we have this inequality. Alpha is greater than alpha not set, if and only if A is greater than zeta over 2. And we establish non-admissible secret pair for only for the inhomogeneous part of the equation. Here, LA rho and LA tilde prime with this relation. And working on the equation, we can close some estimates to show that if the initial data is sufficiently small with this norm, so we keep the linear part as it is, we don't touch, and we show that we have global existence. And this result improves the result of Guzman, which is proven for this range of alpha. And we do not need all the these couple sigma and rho. One couple suffices to deduce the result. So some examples of this initial data. The first one is when phi is in each one sufficiently small. Then we have global existence here in R. We have to verify that the condition not in zero infinity, but in all in R. And this follows by Sobolev embedding and by Sirkat's estimates. Also, we have this example for phi in H1 intercepted with L rho prime infinity. And we can show that this quantity is finite. So just we need to take it sufficiently small, this part. And in sigmas as well, sigma is a particular space than the one. And as at the same time, and if phi is in sigma and we take U naught with this oscillation, we can show also that we have a global existence for this type of initial data. So for this oscillating initial data. So now I will turn to scattering results. So scattering results means that the solution is asymptotic to some function, some data phi plus in some space, so that we have this limit. And in the case of H1, we can show that this limit is equal. We can put this in this side because we have in H1 this quantity is conserved. And to show the scattering, we have to show that this function has a limit in this space, and we have to control this part. For this, so we establish a criteria for scattering, and we take n greater than 4, b between 0 and 2, and alpha strictly smaller than, here we are working in H1. And k, we suppose that is satisfied that is smaller than this, that the gradient of k satisfies also this inequality. So if we have a global solution so that it belongs to this space, LA and alpha plus infinity, then the solution is in all admissible pairs as P. It scatters in H1, and if U naught is in sigma, then also it scatters in sigma. Another thing, if U is in H1 and global in LS, so we add some condition on K, and we suppose that the gradient also is like K, so that we have some regularity near the origin, so we can reach n greater than 1. And if U is in this space, LA rho, and for the other case, we suppose also that we have some singularity, then U is in all admissible pairs, it scatters in each one, and if the initial data in sigma, scattering holds in sigma. So we apply now directly this scattering criterion for the solution with oscillating initial data. So the solution became in this space, so it will scatter. And another thing, application is when we take k is equal to 1 over 1 plus x squared. So with this potential is in L infinity. And when we look to this as an element of an infinity and apply results of standard Schrödinger equation, we will find that we have scattering for initial data in H1 here and in sigma here. You look at this term as an element of L infinity, we apply the standard results for analysis. But since this potential satisfies many decay, it decay with x to the power minus 2 and x to the power 0 as a constant. So it have different decays. So we may apply the result we obtain now with alpha 0 of b with these different decays, and to improve the range of alpha here. So we can arrive at here. Let me continue. So what we have. So we will take k of x equal to this particular value. Sigma here, you can see it is the decay. And alpha is there. So there is regularity. So we have the standard NLS. So we can show if alpha is greater than 4 minus 2 sigma over n, we have scattering. In particular, if sigma is greater than 2, this quantity is negative, so scattering for any alpha. And in sigma, we have to use alpha naught, and alpha naught will be the minimum of sigma and 2. In particular, if sigma is greater than 2, the minimum will be 2, and alpha naught of 2 is equal to 0. So we have scattering for any alpha positive. And if also we take oscillating data in this manner, we can show that scattering holds also for this quantity. So I have to prove, for example, for the example k equal to 1 over x squared. So we have that k is in Ln over b infinity, and the gradient as well. And this is for any b in this range. So we fix alpha in 0 over 4 over n minus 2. And we choose b so that we can put this alpha here. Once we have done this, we work with this b for k of x having this decay, and we obtain scattering from small initial data for any alpha in this range.
What is the relationship?
Yeah, sigma is general, meaning that if you want to go larger than 2, it is so for this it is up to 0, but the other one you have to stop with the minimum of sigma and 2. For the other one, this I take sigma, it may be greater than b. B is nothing here. B is to measure the decay, or the here the decay of the potential. Okay, it may go then b. It may be greater than 2. B for me is between 0 and 2. And I have applied.
Potential is something like x 1 over x to the c, something like that.
Yes. 1 over x to the power sigma, yes.
You're applying the results for b.
For the b, which is between 0 and 2, and it may be singular, I use this homogeneous potential. Here, sigma, it may be any number. For example, I may take sigma equal to 2. B is another thing. B is between 0 and 2, with which I have to measure the smallness of the initial.
So the singularity is coming from infinity or from 0? Because x minus b can be.
Yeah, yeah.
Clarify more.
Yeah, I'm coming here. There is no singularity.
There's some decay at infinity.
Yes.
Right?
Yeah, we can combine both. Singularity near the origin with the power x minus b1 and some decay at infinity. But we have to add this condition. We are not really free to do what we want to do. Okay, and the gradient satisfies this. So we have to take alpha, but between these two numbers. B1 is which measure the singularity near the origin. And B2 will measure the decay at infinity. So the largeness of alpha here is the decay will determine the smallest value of alpha that we can take. And here we measure the B1 so that we have the maximum value of alpha. And we have to choose B between these two numbers. The B is the number with which we have to measure the size of the emissive. Okay. Okay. And we find epsilon depending on B1 and B2. And the proof, as I say, since we have B, the alpha naught of B have some is decreasing with respect to B. So we apply this result to this type of potential to choose the appropriate B. And we have, as the potential decrease at infinity, for example, when B2 became more and more large, the range of alpha giving scattering became wider or large. So now I turn to the defocusing case, and I will take the value k of x equal to x to the power minus b. So we have global existence. We do not need smallness of the initial data. And to apply the criterion of scattering, we have to show that we have this belonging to this space LA, L alpha plus 2 for this quantity x to the power minus b over alpha plus 2. So we have to do some decay estimates of the solution. We have to prove that the solution of the defocusing case, which is global, satisfies this decay. And this decay is proved by in this case, but using Lebesgue space and so on, and we found that we can do this decay, but still for alpha greater than alpha naught of b, and the alpha naught of b becomes from this condition, so that we have some anti-gravity affinity. And we have that the solution, we can show with this decay, the solution becomes in this space, so it scatters. And here we have alpha strictly greater than alpha naught of b. Okay. So let me now return to this case of alpha equal to alpha naught. For the defocusing case, we can consider the case n greater than 3 with this particular potential, and alpha equal to alpha naught. For this, we have to do the pseudo-conformal transformation, and we have to work with the this equation obtained with the pseudo-conformal transformation. Also, we can, in sigma, we can show scattering for small initial data up to this number for in positive and negative direction of time. And as well, we can show scattering in some other space, sigma s, which will measure some decay. And sigma s is this space sigma, but we impose that V grad V and X V is in H dot S, and S is in some S 0 S naught, and this the smallest value of alpha here is this alpha tilde of B, which is obtained when we take S equal to S naught. And unfortunately, this alpha tilde B is still greater than 2 minus B over N. And it is greater also than 2 minus 2B over N. Why these two numbers? First, when we take B equal to 0, B equal to 0, here these quantities are equal to 2 over N. And we know by Barab results that we have no scattering in the case of real coefficient in front of the nonlinearity when alpha is smaller or equal to 2 over N. Okay, so this alpha naught, we think that we have to reach this number. This is the Barab part for the equation with x to the power minus b, and it is, we have wrote this with Greer, but this number is greater than even this number, and we actually we cannot reach this number 2 minus 2b over n, so that we have scattering for small initial data for this quantity. On the other hand, we have proved that we have also self-similar and asymptotically self-similar large tail behavior, which is different from this context. So now I will move to.
So this is also holding for when the coefficient is constant.
Constant, yes. Yes, I think yes, yes. You take b equal to 0.
Over there, you use that b is positive, right? You know.
Yeah, this is it. This, yeah, you replace b by 0. This I think is okay, but this is not true. Meaning we cannot see the difference between 2 minus b, 2 minus 2b. We have now these two exponents. This is for scaling things. And I did think this is some L1 log property for blow up for the George invariant Schrödinger. So for B strictly positive, this is strict. Yeah, but this is an observation just that for B positive, there is a difference between these two. We don't distinguish between those two numbers if B equals to 0.
So before we go to the next part, in the slide 37, I wanted to see, for example,
Yes.
yeah, how you choose B1? An example of value in B1.
B1 and B2
Satisfying the last condition.
yes, this condition. But we have to add this property.
Yeah. An example of value.
I can say take B1 equal to 1 and B2 any number greater than 1. We have some. So then so I will turn now to the dented EMLS, and in this part, as we have treated, I think for the x to the minus b, I will present in more detail x, the case b equal to 0, because even for this case there is many things that are not known up to now. So here, when A equal to 0, say also B equal to 0 or positive, then we have for the focusing case, meaning the case where we have possibility of a blow up, and this is done by Genie, Berbelot, Glacé, and Tsutsumi. And for global existence, if alpha is smaller than 4 minus 2b over n, there is global solution, and there is solution that do not scatter, as I said before, by Barat. So we have to understand what is the effect of the damping A on the global existence and on the scattering results. So we have these two quantities for the damped ENLS, the L2 norm and the energy. And when we take the derivative with respect to the norm L2 of T, we have that is 2 minus 2A and minus A, which is positive, multiplied by some K of U, which is given by this. If, for example, we have mu is positive, this quantity is positive, and this quantity, the energy is decreasing, and the norm L2 as well have exponential decay. And we have, in this case, global existence, so there is no problem. But if mu is, for example, equal to -1, although the norm L2 is decreasing, but it is not clear that if the energy is positive, if the energy is negative at time t equals 0, it's still negative for positive time. So the question is it possible that the damping term will arrest or will stop the damping? And in the literature, they consider these two quantities, which the first one is the variance, V0 at the instant t equal to 0, and one is the weighted norm. And here we consider U0 in sigma. And we have these three conditions of the first one, if the energy is negative, the second one, if the energy is equal to 0 and the variance is negative, or if the energy is positive and the variance became more negative, then we have some some blow up results. The first one, when A equal to B equal to 0, meaning the classical Schrödinger equation. It is proved by Glacé and by Tsutsumi for A positive, meaning for the damped case. We have a blow up to some coefficient A star naught, which depends on the initial data. And we have in this case that the blow up time is finite. After that, Horta and Todorova, for A positive and B equal to 0, they show that there is two lambda of damping, A dot as A sub dot, which is positive, such that if A is smaller than A sub dot, the maximal time of existence is finite, while if A is larger than A dot, then the solution is global. And we do not know if this quantity is are equal or not. Okay, and for A positive and B positive with the Jberi and Alwi, we find some lower estimate of A naught of U0, and we find an estimate of the maximal time of existence with respect to A in this manner. This is A, but we divide by this component, and this is the maximal time of existence for the first case when the energy is negative, and here when the energy is equal to 0 and the variance is negative. And we find also the other value. And we show if the variance becomes more and more negative, the damping value giving rise to became more important. There is a numerical study done by Fibish in the critical case of alpha and dimension 2. And he proposed that, in fact, there is A star, which is the same here and here, so that up to A star, we have blow up. And after that, there is global existence. But this is not proved rigorously. And there is no analytic proof for this things. And using this Fibish conjecture that the function T max, U naught depending on A, is in fact monotonically increasing for A smaller than A star. And there is some references after that, in particular this one, studying the monotonicity of property of the blow up time, show that there is no monotonicity in some cases. And
What is the monotone again?
this one.
Can you go back? What is growing?
The maximal time of existence with respect to the damping coefficient A. So he claimed that when A becomes more and more important, we have the chance to have global solution. Okay, so the maximal time in increasing, so up to infinity when we meet A star. We have A star. All these are just conjectures. We have A, we fix the initial data, we vary the damping. At some time, we have global existence. And the time of blow up will increase, go to infinity. This is just a conjecture.
Yeah, that's exactly what we're doing. So the blow up time goes from infinity when I goes to infinity. That's what
The blow up time?
yeah, it goes from infinity when I goes to infinity. That's the point.
Yes, when
So when I goes to A star.
so A star, it became more and more greater than. But just the conjecture, it is not still numerically. Still numerically, these are done by Bliss, Karl, Smolzer, and these are just calculation. There is some initial data where here I don't see this is the parameter A and this is the blow up time. This is increasing for some initial data, but here there is no monotonicity for the blow up time. Okay.
And this would be dichotomy of thing that we can find, for example, look for A, for which we have global existence. So when A is very large, we expect to be with global existence. So we expect that we have this connected set. But this is one connected set, or it can be.
But I don't know. They expect that I think it is possible.
So this is an open set, you get it.
Yes,
And
it
it remains to show that this is a included set.
Yes.
This is like Navier stocks.
Yeah. Yeah.
And
And
Few minutes.
few minutes. So I will maybe just what we do for Tmax, we show that we can find some lower bound estimates in terms of A, and we verify, in fact, that this quantity have no monotonicity. I will say some words how we do this. At the same time, when A is greater than this, we have global existence. So we can find something how A is large with respect to the initial data, so we have global existence. Okay, and we can also show that the decay with the damping can be estimates with more decay depending on alpha. Let me show how to do at least these two things. Is just on working on the equation, and instead of neglecting the term here, depending, so we have to transfer this equation with v instead of u. We multiply by this exponent, and we find some function h for v, and this function h is given by this exponential. But instead of neglecting this, we give the importance for this property, and when estimating, we calculate this norm of h, which is given by this quantity, and with using this, we can find an estimate of the maximal time from lower estimate for the maximal time of existence, and this will give us this property. But still some open question, and maybe these are the more important, is to show that A star is equal to A star sub equal to A star 4, and to study numerically or find an upper estimate and good lower estimate. We think that this lower estimates is maybe it is okay, but the upper estimates is not clear to find the optimal estimates and the monotonicity of this, the maximal time of existence with respect to the data. So I will stop here. Thank you for your attention. So thank you for coming.
For the lower bound that you get on the time, it seems that it is with the not increasing with the right?
And there is no decay, and it increase and decrease. It is not.
You have 1/8.
There is a logarithmic on this quantity. It will depend on these constants, and Q naught is in the numerator and in the here and here. So this quantity really is not monitored. But I think it will depend on initial data. So in some class of initial data, maybe it will be monitored. In other classes, maybe it will be different.
No, I'm asking that.
Oh.
I was asking that.
So in dimension 2, when we take mu equal to 0, we know the fundamental state.
Yes. Yes.
So inside the body of global existence, and we start to blow up from the bond.
Yes. Yes.
And now when we move a little bit this one, we know exactly what's happening when your coefficient is small. Or can we?
No, really, I don't know. I see. For the critical case, for L2 critical
Yeah, this
case.
is the conjecture that you put for cubic 1 and there this conjecture for dimension 2.
Yes.
For the cubic case for dimension 2, and you put A and before.
Here,
No, before.
this one.
Yeah.
Yeah, this
So
is
for
the,
A is 0, we know what happened.
yes. For A positive,
And even for A small, we can construct this fundamental state and we can generate blue up.
I think. No.
Because A is simply positive. Because you mentioned the pseudo-conformal transformation.
Yes,
So
yes.
it will be destroyed, this one.
Pseudo-conformal transformation with A. There will be a coefficient. Yeah, it is. So we have to work with V, which is A or AT. We obtain the same equation, and
Perturbation, we can.
Yes, 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 yes. Mm. This is important. Mm. Mm. But what do you think about this? Is it possible to obtain this?
Huh?
So to show that there is A star, capital A star, separating into components.
Yeah, so I think we start when we are close to zero, we start to see blow up.
Yes.
We said one is very large, so there is no blow up.
Yes, yes.
So now, so we can push this blow up to some, or at least some interval, I don't know, for that, it's critical.
Yes.
And,
Yeah.
Are there any branch, I mean, are there any branch of blow up that will go from zero? And we can practice this branch and to see.
Mm. So because
So it was conjectured how many years? So it's
23 years.
1 3 years? The series, the Friday,
No, 23 maybe it's not a lot. Maybe 100 years. No, I think it is possible to do I think it's possible to show this,
But you don't have this intermediate machine.
Yeah.
Have
Yeah, but it's intermediate, so-
and follow up for different initial data and stuff like that. Fast.
yes. It's not good.
Yeah, but you get a start to depend to U0 to your initial data. So
Yes, yes.
we have the same, the same.
You fix the initial data. No, so you fix the initial data and you have to see.
You have to
this
see
data.
when you move the.
Yeah.
So we don't know nothing for even show this one.
Yeah. But I think for this, maybe we have to introduce new methods because up to now, the blow up is done using classical idea for the non-damped intuition. And the damping, even for x to the power minus b, have an effect on the blow up. For example, for the Schrödinger equation, some results on each one mean the radial symmetry. When we have decay, we can suppress this condition with x to the power minus b. So I think we have to change how to think or how to prove blow up in this region. And some results on continuous dependence with respect to A will be helpful, I think.
What were the results for A equals 0? This gives always blow up, is what you're saying.
Oh, yeah, there is many results I have cited.
For A0, this standard Schrödinger.
Yes.
You have a big bar, so if we have the fundamental state, if we must take this global resistance, we have just this boundary, which is the mass. But after that, it can, we don't know.
So this is region is not.
It is not clear. It is not.
That's what I'm saying. I think
So
it's
thank you very
clear.
much. Yeah. Thank you. Also the